This is a lesson on the ideal gas law in the heat and thermodynamics unit. The inverse gas law relates the pressure, volume, and temperature of a gas to the number of molecules that are there and the Boltzmann constant. And so this is the equation right here. This was derived in 1834, if you can believe that. It was theoretically derived. You can see in the equation that there's a pressure, a volume, a temperature, T here and T here. N is the number of molecules. K is the Boltzmann constant, so you could put a B there. And so this is the number of molecules. You would use K with the number of molecules. If you knew the number of moles, that's N, you would need to use R, the universal gas constant, instead of KB when you use this equation. It's a very straightforward equation, and it actually has energies of units. P times V, pressure times volume, has energy joules. When you take K times T, well, we already know that. KT with the kinetic theory, this turns out to be joules when you multiply these all together. So this is a relationship of energy of the pressure and volume to the temperature and the number of molecules that are in that substance in the container. Very interesting equation. The ideal gas law is for gases. You cannot use this equation for solids and liquids, which is why I have not taught it yet until this point. I have seen students want to use the ideal gas law on solids and liquids, and you cannot do that. This is good only for gases. So watch out when you're applying this equation that you're looking at a gas only. Let's do an example of the ideal gas law in a problem. I picked one that would show us how many oxygen molecules are in your breath. On average, a human takes in about 4.6 liters of fresh air during a normal breath. Fresh air contains approximately 21% oxygen. Okay, so I see a couple of numbers here. Of this 4.6 liters, 21% is oxygen. Assuming that the pressure in the lungs is 1 atmosphere and that air is an ideal gas at temperature 300 Kelvin, find the number of oxygen molecules in the normal breath. Okay, so we want N. They don't care about number of moles, so I'm not going to use that form of the equation. I'm just going to solve this for N. N equals pressure times volume over K times temperature. There is 1 atmosphere pressure, so I know pressure equals 1.0125 times 10 to the 5th pascals. I'm going to put it in SI. The volume is 4.6 liters. And I know that 1 liter is 0.001 meters cubed, so I can get the meters cubed and SI out of there. They've given me the temperature in Kelvin, and I know K. So I'm going to go ahead and plug in some numbers. 1.0125 times 10 to the 5th times the volume, 4.6 times 0.001. And then I'm going to divide by K. K is 1.38 times 10 to the 23rd, negative 23rd. So negative 23rd. Times 310 Kelvin is the temperature. And when I run this through the calculator, we get 1.09 times 10 to the 23rd molecules in your breath. That's how many molecules are in your breath. What we need to do is figure out how many of those are from oxygen molecules, the number of oxygen molecules. Well, I know that it's 21% of the total number of molecules. So when I take 21% of 1.09 times 10 to the 23rd, I get 2.29 times 10 to the 22nd O2 molecules, which is a lot. While I was here with the ideal gas law, I wanted to introduce the idea of the thermal processes in conjunction with the ideal gas law. And a little bit of history here is that the ideal gas law has been studied in increments, in little parts by different scientists through time. Charles studied this as isobaric or under constant pressure. Boyle studied this under isothermal or constant temperature. Gay-Lussac studied this under isochoric or constant volume. So you will see these laws be talked about in different ways, maybe in chemistry. Adiabatic is the other type. So these are the different types of thermal processes, and we will study these more as we study thermodynamics a little more. We can quantify them with the ideal gas law if we're looking at a gas. And how do we do this? When I look in here, I see that there's a constant, and if I am just looking at the process of a gas in a container, I know that the number of molecules won't change either. So if I solve for one side of the equation to be a constant value, no matter what, so we have NK, those two things aren't changing, I would divide T by both sides. I get PV over T on one side, and this is a constant value. No matter what pressure, volume, or temperature I'm at, I will be able to have a constant value. These will all correspond one another. If I have a higher pressure, I'll have a lower volume at the same temperature, etc. So what we can do is say, okay, well, if I have one state of pressure, volume, and temperature, it must be constant in proportion to another state of pressure, volume, and temperature. And so this equation is frequently used in conjunction with the thermal processes. If I'm under constant pressure, P1 equals P2, and that gives me the equation of P1 and is equal to P2. I get V1 over T1 equals V2 over T2, which is Charles' law. So nothing magical there. It's just taking whatever is constant and considering that in this combined gas law. And so this is a useful equation to use if you have a gas undergoing a process. Remember, with different processes, different things are held constant or not if you have an adiabatic process. So watch out for that, and we will study this more in thermodynamics. I've selected a problem for us to use the combined gas law, which I've written here. An ideal gas, so C, ideal gas, that lets me know I can use this equation. At 15 degrees Celsius and a pressure of 1.7 times 10 to the 5th pascals, occupies a volume of 3.1 meters cubed. If the volume is raised to 4.8 meters cubed and the temperature raised by 30 degrees Celsius, what is the pressure of the gas? What's the new pressure? Okay, so we have a lot of things going on. I'm going to write out my information to kind of sort out what's going on. An ideal gas, I have an initial temperature, T1 equals 15 degrees Celsius. I'm going to remember, however, that the KB, remember the Boltzmann constant is in Kelvin. I have to do this equation in Kelvin. So I'm going to add 273.15 here, and I'm going to get 288.15 Kelvin. I have a T2. It's raised by 30 degrees, so I have 15 plus 30 plus 273.15. So I'm going to add 30 to this number, which will be 318.15 Kelvin. So those are my two temperatures. I'm going to keep working through here. I have two volumes. V1 equals 3.1 meters cubed and V2 equals 4.8 meters cubed. And P1 equals 1.7 times 10 to the 5th pascals. So I've kind of identified all of the quantities I need to go into the equation, and I'm solving for P2. I'm going to solve for P2 algebraically. P2, I'm going to multiply both sides by T2 over V2. T2 over V2. So that cancels them. So that cancels these terms on this side. And I'm left with P1 V1 T2 over V2 T1. Interesting. Okay, so be careful with your algebra. I see students get sloppy there and just go V1, T1, V2, T2, and get that mixed up. And what I'm going to note is that I have a couple of proportions as well. So even if my volumes were not in the same units, if they were in centimeters cubed, for instance, or if they were in liters, it wouldn't matter because it's a scalar and that would cancel out. I still need my temperature in Kelvin. 15 over 45 is not the same of 288.15 over 318.15. I can't just do that with the Kelvin. So I need to change those to from Celsius to Kelvin to make sure I have the right units to multiply in here. So P1 is 1.7 times 10 to the fifth. I have a ratio of the first volume over the second volume, so I have 3.1 over 4.8. And then I have a ratio of the second temperature over the first temperature. So I'll go 318.15 over 388.15. When I run this through the calculator, I get P2 is 1.21 times 10 to the fifth pascals. Okay. I converted this to ATMs just to get an idea of how many atmospheres this is, and it's 1.197 atmospheres, which seems about right. It's not an astronomically large number, and it's also above 1 ATM, which I expected. When I think about the type of thermal process this is, all of the quantities changed. Nothing was kept constant. So this is an adiabatic process. Adiabatic processes happen in clouds. They happen all over the place. Actually, it's really hard to keep one of these quantities constant. So you will see adiabatic processes more frequently than any other process, but we will study the other ones in thermodynamics, as I mentioned.